Hey guys, Miss Crutcher here. Sorry, can't be with you today with the SAT testing going on, but still want to keep you guys caught up with the rest of the classes. So you just need to watch this little video, take notes on it, and then do the homework that is listed on the packet. I'll be checking it next class. So what we're going to look at today is a little bit more about voltage and electric potential energy and capacitance. So if you think back to potential energy, remember potential energy is stored energy or energy based on a distance. So the first thing that we're looking at today is that when a particle moves from one plate of the same charge, so you have a positive plate, starts on a positive side, it's going to try and move to the opposite side, because remember it's going to want to repel away from the positive, be attracted towards the negative, so it would travel across the electric field to the other side. As it moves from the positive side of the plate to the negative side, it's going to lose potential energy because it's going to decrease that distance from the other particle that it's attracted to. The same thing would be true if you were looking at a negative particle trying to go from the negative side of a plate to a positive side. So with electric potential energy, we're always looking at the fact that you're going to lose potential energy as you travel from the same side of the plate that you're charged with to the side of the plate that you're attracted to. We're never going to look at a positive trying to go towards a positive side of the plate or a negative trying to go to the negative side of the plate. In order to find the potential energy for this loss, for this movement where it's going to go from positive to negative or negative to positive, we use the equation that your PE electric, so we're talking electric potential energy, is equal to negative QED. Again, the negative sign is just telling us that potential energy is lost because you're decreasing that distance. The distance that you are from where you originally started to where you ended up is getting smaller because you're getting closer to the particle that you're attracted to, or the side of the plate that you're attracted to. Q, if you remember from the other day, has a unit, or is represented by charge. The unit for that is C for coulombs. Your electric field is going to be represented by the letter E, and it's measured in newtons per coulomb. And then finally, D is going to be the distance the particle moves, measured in meters. Okay, so if they give it to you in centimeters, make sure you convert that, okay? And if you think PE is going to be represented, is going to represent your potential energy, and the unit for that is joules, just like the other energies and work that we looked at in the past unit. What we're looking at next is the idea of electric potential, which is very similar to your energy. So electric potential we look at is basically looking at energy for a certain charge. Okay, so for a unit of charge. So potential, electric potential, which is represented by the letter V, is just an energy per charge. So instead of looking at it in just the terms of like how much energy you have, we have to look at it for a certain amount of charge that we have. So voltage, electric potential, is just a very specific version of energy. Because we factor in this unit of charge, the unit for voltage is V. Remember that the unit for potential energy is joules. And the unit for charge is still coulombs, okay? So you're really going to want to know your units. That way as you're working through these different problems, look at the units and that will help you figure out what variable you have. So what potential is, okay, is we're only going to use it anytime we're looking at a difference, because what we want to see is what's going to happen as that energy is changing. Okay, so with a voltage, we're going to notice that we're going to start out with a certain amount of voltage on one side of like a battery, and the other side of a battery, if you look at a battery, it has a positive and a negative side. So we would be actually looking at what's going to happen as you go from the positive to the negative. So we're looking at a journey. Where is that charge going to travel? So what that really means is that your delta V is going to actually be a potential difference. So you have numerous different words for this delta V. You could call delta V voltage. You could say that it's the volts. You could say that it's the potential difference, or you could call it potential. Okay, all of those words mean V. Okay, which is, I know, is kind of confusing. Okay, because we want to see what's going to happen to the charge as it moves around the whole thing. Potential energy, or potential difference, like I said, is measured in volts. Capital V. Okay, this is the easiest one that you're ever going to see. Because if you were to write out something, you would end up with like a V, a potential difference, potential, a voltage of, let's say, 5 volts. So you would write V equals 5 V. This is like the only variable you're ever going to see where the symbol and the unit have the same letter, which makes it really nice for you guys to remember. A volt is represented as a joule per charge. So what that means is that as a 1 coulomb charge moves through a potential of 1 volt, the charge is going to gain, really it's going to lose, 1 joule of energy. Since a volt is a joule per charge. So that's what we're talking about this journey. You're going to start out on one side. It's going to move through the potential difference, the potential difference being a battery, and it's going to lose energy as it wants to go from the positive side of the battery back to the negative side. Remember from the last unit that your change in potential energy is also equal to the work done. So if we could look at to see how much work, remember work is your force times your distance, so we're looking at how much work does the battery have to do in moving that charge around. So we can substitute work, given that work equals delta PE. And from the last equation that we wrote down, where your potential difference, or your voltage, equals this PE over Q, I can plug this relationship in and come up with this new equation. So I could also have that your delta V, your potential difference, is equal to work divided by the charge. So it's just another equation that you can use depending upon if you're given the potential energy or the work. It's meant to make your life a little easier. Okay, a couple examples of a potential difference would be an electrical outlet. So when you go to charge your phone, it's going to start and it's going to emit the charge on one side of the device. It's going to cause all those electrons to start to move. It's going to go into your electrical device, and then those charges are then going to move back to the other side of the outlet, and it's going to be running in like a continuous circle. You also have your battery terminals. Like I said earlier, look at a battery. You have a positive and negative side of a battery. So when you put them in an electrical device, you have to make sure that you always get the positive and negatives lined up correctly. Okay, that's a big thing for those. You could also say an example of this would also be like a generator. Has a potential difference. So like when the power goes out, you can use a backup generator. Anything that really supplies power to something would be an example of a potential difference. Okay, Another equation that we end up getting for potential difference, this is when we're talking about a uniform electric field. So this would be like from something like a dipole, where you have an equal amount of positive and negative charges on the two sides. You end up getting the equation that your potential difference, this delta V, is equal to ED. Okay, D is going to be both the direction, okay, and the distance, okay, that the charge would have traveled. Okay, so with this, we have to look and see which direction it's going, because remember, some of these quantities are vectors. E, remember, is the electric field. So going back to these all-important units, delta V is measured in volts. E is newtons per coulomb, which is represented by your electric field. Those lines of field, lines of force that you were drawing the other day. And D is still measured in distance. So again, just a different equation depending upon what variables you have. Your potential scalar, okay, so again, if you think back, scalar versus vector, scalar quantities just have a magnitude, so you don't have to worry about the direction. What that also means is that if you have a negative charge, you don't have to put that negative. You still have to use the negative in an exponent, like a 10 power, because that's telling you that a number is really small. But if you said that V was to the west, you don't have to worry about it, okay? Treat them as positive. A battery, okay, specifically, is made up of two different terminals, a positive and a negative. The negative terminal of a battery is actually the ground, because it has a 0 voltage. The positive terminal of the battery is whatever it says on there. So if you look at like the AAA batteries that are in your calculator, okay, they're going to tell you a certain voltage, like 1.5. That would actually be the voltage on the positive. So remember, we talked about potential difference, because you're going to have two different terminals and it's going to travel. So you're going to start out on the positive side of the battery with that 1.5 volts. You're going to move all the way around to the negative side of the battery and return with the 0 volts, because you've used up all of that energy during the transition, during the travel. Things always want to go from the higher to the lower. So they're always going to start on the terminal that has the higher amount of potential and end on the terminal that has the lower amount of potential. Okay, that works for everything. Generators, electrical outlets, they all work the exact same way. One of the things about a battery that people get confused about is the idea that batteries supply charges. Okay, they don't supply charges to the wire, to the device that they're going to charge. Those are all already there. Okay, the wire has tons of electrons already sitting there waiting to move. All the battery does is give it the energy that it needs to move. So it's going to add energy to the system, that potential energy, and it's going to allow then the charges to start to move through that electric field that's created once it's turned in. So a battery is not like this endless supply of charges. Okay, a battery is an energy. So it gives the electrons an energy to move. Okay, it's kind of like feeding you guys. Okay, you guys need food in order to have energy, so that way you can move. A battery needs has energy, and it supplies it to the wires to give those electrons a chance to move. That's why batteries die. They don't die when they run out of charge. They die when they run out of energy left in them. Okay, the last thing we're going to look at today is the idea of a capacitor. What a capacitor is it's something that's going to store charge to use later. So unlike a battery where it just has that energy waiting to be used. With a capacitor, what you're going to do is you're going to charge it up from a battery or something or some other device, and then it's going to hold that charge until you're ready to use it. The other thing about it is that a capacitor is going to deliver the charge really, really fast. So once you hit the power button on that capacitor, it's going to use all of its energy really, really quick. Okay. Camera flashes. Okay. If you think especially back to the old disposable cameras, you'd sit there and you'd wind up the camera, get ready to take a picture, and then you'd have to charge the flash. While you're charging the flash, you're storing energy. Once that energy is stored in the capacitor, it's ready to go. You could take the picture right then, you could wait a little while, but the energy is going to be there. And then as soon as you hit, would take the picture, hit the flash button and actually take the picture, all of that charge would be gone. So you'd use all of that stored charge that it took a little while to build up in an instant. Okay, the only difference is that now your phones that have the capacitors on them to take pictures, it just charges really quick, okay, compared to like the old disposable cameras as technology has changed. You have strobe lights, okay, do the same thing. They use all their charge real quick, so you get a really big flash of light. It takes a second, and then it charges again, and then it uses all their energy. So what happens is that for any capacitors, they're going to have their energy being stored, so that way, like if the power goes out, your computer will take a second, since it has a capacitor built into it, to store the energy, to store things before and immediately goes out. Basically trying to make it so that way if you had a power outage, your computer like wouldn't fry right away. Okay, it wouldn't immediately lose the power. Trying to make it not as sensitive. The thing about it is, though, most of you guys use laptops instead of desktops nowadays, so laptops aren't as sensitive to that, since they don't have to be plugged in all the time when you're using them. What a capacitor specifically is made up of is, inside of a capacitor you have two metal plates. One is positive, one is negative, and it's separated by some sort of difference, some sort of distance, creating a uniform electric field between the two. So here you have a row of electrons, you have a row of protons on the other side, and that's what it would look like. You have a metal plate on the top, a metal plate on the bottom. It could be positive and negative, top to bottom. It could be flipped the other way, and then it's separated in the distance. So it's going to store the charge and then use it. One plate has to be positive, one plate has to be negative. These two plates, the metal plates, are going to be the same size. They're going to have the same magnitude of charge on them, just one's going to be positive and one's going to be negative. Again, creating that that uniform electric field. It's going to create an electric dipole, since you have equal amount of charge on both things. Alright, so your equation to find a charge stored in a capacitor is Q equals CV. Q, right here, this capital Q, represents your charge measured in coulombs. C is going to represent your capacitance. Okay, so basically looking at how good your capacitor is, how much can you store on that capacitor. The unit for a capacitor is measured in farads, which is represented by the letter F, capitals for all of these. And then V is going to be your voltage. So your capacitor is going to be based on whatever device it's going to charge it up. Okay, let's try and work through a sample problem. If you look at 24, it says that a capacitor of 1 microfarad, remember this cursive mu means micro, has a potential difference of 2.0 times 10 to the negative 5th volts. What is the charge? Start it out the same way you do all your problems, write out your givens. Okay, if you notice, this micro means 10 to the negative 6th. So I have to convert 1 microfarad to just farads, okay, because that's the scientific unit. So micro means 10 to the negative 6th, so this is going to become 1 times 10 to the negative 6 farad. My potential difference is my voltage, that V, 2 times 10 to the negative 5th volts. Okay, I am looking for the charge, the letter Q. If you want to put lowercase q versus capital, it's fine. I mean the same thing. Okay, switch them however you want. Okay, I'm going to use the equation that I just gave you on the previous slide. Q equals CV. I don't have to manipulate the equation since I'm solving for charge, so plug it in. 1 times 10 to the negative 6 times 2 times 10 to the negative 5th becomes 2 times 10 to the negative 11th. We drop the 1 out on this term because 1 times 10 to the negative 6th, anything times 1 stays itself, so 1 times 10 to the 6th is really just 10 to the negative 6th. And then make sure you add your unit of charge. Okay, look at the front page of your packet to see the rest of your homework problems. I did post a bunch of solutions online, so feel free to look at that and stop by for tutorials if y'all have questions. If not, have a good day, and I will see y'all on Friday.